So continuing our video series on linear algebra, I'd like to cover in this video some basic matrix operations, or put it simply, matrix arithmetic. And the pertinent sections in Wessel's notes are 3.3 to 3.7. So let's talk about how we add matrices. And as you've used MATLAB before, you're probably pretty familiar with this, but at least for vectors. But put it simply, if we add matrix A to matrix B and we get a resulting sum matrix, the operation is simply carried out by adding each element of A with each element of B, and that gives the sum of those two gives each element of C. Again, the element ij is the ith row and jth element of A. One restriction of matrix addition is that A and B must have the same order. Again, the order being defined by the number of rows, m, by the number of columns, n. Now let's talk about the dot product of two vectors, and I know you've worked with this many times before in various contexts, but I'd like to sort of formally define it here. So if we have two vectors, say A and B, then the dot product, and I'm going to use the transpose to make A into a row vector to take the dot product with B, which is a column vector. And we can describe that mathematically by the sum for I equals 1 to n of the ith element of A transpose and the ith component of B. So to describe that operation visually, let's look at an example of two vectors that are 3 elements long. So the dot product is defined for the transpose of a vector on the left-hand side and a column vector on the right-hand side. And I like to think of it as sort of moving the row vector across and then folding it down onto the column vector. So the first element of the row vector matches with the first element of B, the column vector, and we get A11, B11. And remember, we're summing it, so it's A1, B1 plus A2, B2 plus A3, B3. And geometrically, we can think of the dot product as the magnitude of A, which is the same as the magnitude of A transpose, the magnitude of B, the length of those vectors, times the cosine of the angle between them. Okay, so if A and B are parallel, then the dot product is just simply the product of the magnitudes. And this gives the maximum dot product of any two of these two vectors. If A and B are perpendicular, then the dot product is 0, right? The angle between the two vectors is 90 degrees, giving 0. And you know what? I should use orthogonal. Perpendicular, I'm pretty sure, is sort of restricted to a geometric definition, whereas orthogonal is more general. So, you know, in 3D space, we can think of two vectors in 3D space, but oftentimes vectors are much longer than n equals 3. They can be, you know, 100 elements long. So we're dealing with multidimensional space, for which orthogonality is still defined by this dot product being 0. So that's a matrix, a multiplication between two vectors. Let's talk about matrix multiplication in general. So we could describe C as being equal to the product of A and B, and we can write matrix C equivalently as C sub ij in square brackets. So this represents all the elements of C, and the brackets mean it's a matrix. And so the ijth element of the vector is the vector product, vector dot product of the ith row of A with the jth column of B. So I can write that out as follows. So Cij is equal to the product of the ith row of A, and I'll write that as a vector, and the transpose, that'll make this vector a row vector. So this denotes the 8th row of A dotted with the jth column of B. And as you recall, our vectors are by default column vectors, so this will denote the jth column of B. So let's write this out. And so we'll consider a 2 by 3 matrix for A. Right, the first indice denoting the row and the second indice denoting the column. And we have to multiply that by a 3-row 2-column matrix of B. B1, 2, B, the second row, first column, second row, second column, third row, first column, third row, second column. And let's write that out. So again, for the 1, 1 component of C, that's the first row, the vector product, or the dot product of the first row of A with the first column of B. And I often like to think about it as taking this first row and bringing it over and folding it down the first column of the second matrix. So that's A11, B11 plus A12, B21 plus A13, B31. For the first row, second column, the 1, 2 component of C. We take the first row of A and do a dot product with the second column of B, again moving the first row over and down the first column of B, and that gives A11, B12 plus A12, B22 plus A13, B32. The second row, first, the 2, 1 component of C involves the dot product of the second row of A with the first column of B, and that is A21, B11 plus A22, B21 plus A23, B31. And then finally, the last component is the second row dotted with the second column. Okay, and so this shows all the terms of the C matrix as an example. So let's look at the dimensions of the matrix we've multiplied. Let's say A is M by P, for example. And in order to multiply A by another matrix, B has to have the same number of rows as the columns of A. So B has to have P rows if A has P columns. And B could be, for example, P by N. Okay, so the key thing is that the two inner dimensions must match. That is, if we write out the dimensions of A next to the dimensions of B, the inner dimensions, when we write that out, have to match. And the other aspect is that C will be M by N. So the product, I guess the two outer dimensions, is, I guess, gives the dimensions of the product matrix. Right? So in this case, A was 2 by 3, B was 3 by 2, and indeed C is 2 by 2. So let me give you a few examples to try, and I'd like you to do this on your own. Stop the video after I define these matrices. So you're going to solve A times B, and I'm asking you to determine what C is in the following cases. Okay, so I've written down the 3 examples I'd like you to work out. So stop the video here and work it out on your paper, and when you're done, go ahead and restart the video. And here are my solutions. So if you've done it correctly, you should get these solutions for the first 2 cases. And of course, the last case was undefined. So let's just verify the dimensions matched up, or we'll illustrate how the dimensions did match up for the first 2 cases. So the first matrix was 2 by 2. The second matrix was also 2 by 2. And so our 2 inner dimensions matched, and our 2 outer dimensions gave a 2 by 2 resulting matrix. In the second case, we had 3 rows and 2 columns times a 2 by 2 matrix, and the resulting matrix had 3 rows and 2 columns. And again, the inner dimensions matched. In our third example, we had 2 rows and 3 columns multiplied by a matrix, we're trying to multiply it by a matrix that's 2 by 2, and these don't match, so we can't do it. Okay. Next, I'd like to briefly cover how we evaluate the transpose of a matrix product. So consider the product of the matrix A and vector X, and we want to evaluate the transpose of that. That turns out to be the transpose of vector X pre-multiplied by the transpose of the matrix A. So to carry out this operation, we reverse the order of the multiplication. We reverse the order of the multiplication and take the transpose of the vector and the matrix. Now suppose we have a product of 2 matrices followed by a product of a vector, and we want to take the transpose of that. Following our first rule, we pre-multiply by the transpose of our vector, of the last term in our product, and then multiply by the transpose of our matrix product. And then we apply our same rule to the transpose of our matrix product. And that gives X transpose A transpose C transpose. And I encourage you to try this out on some examples by hand or in MATLAB. We'll go over how to do matrix products in MATLAB, but I encourage you to verify that these relations are true. And we'll be applying relationships like this when we apply linear algebra to do regression, and that is covered later in this video series. So the last topic in this video is I'd like to introduce the identity matrix. And the identity matrix is written as capital I. And the identity matrix is defined such that when we multiply I by a matrix, we get the same matrix back. And I'm using the double bar to be to indicate that we're defining what I is by this equation. And likewise, we could post-multiply A by the identity matrix, and we would get the same matrix back. So some characteristics of I is it's a square, it's a square matrix, and it's a diagonal matrix. And all the diagonal elements have 1s. And we can write I mathematically using the following equation. So the ijth component of I is described by this delta function, delta ij. And delta ij is the Kronecker delta function. And the Kronecker delta function is defined as a function that is equal to 0 when I is not equal to j, and delta ij is equal to 1 when I equals j. So an example of a matrix I, of course, would be a 2 by 2 matrix for I would be 1, 0 on the first row and 0, 1 on the second row. And so what I'd like you to do on your own here is, why don't you convince yourself that if you multiply this matrix, we can call that A, with I, that you should get that matrix A back. So if you haven't done this already, I encourage you to go ahead and give this a try on your own. I'm not going to go through it now, but you should give that a try. The other thing that you should note is that when you see an equation like I times A times I, then what's implied is that the size or order of I is such that the number of rows of I is equal to the number of columns of A. Now, some of you may have worked with MATLAB more than others, but in MATLAB, a matrix multiplication is denoted as a star, or asterisk, I should say. Or a matrix multiplication is done using the asterisk. So if you wanted to do a matrix multiplication between matrix A and matrix B, you would just write that. And that's in contrast to dot star, which is a term by term multiplication. And this is something we've used already in the class. This is a full matrix multiplication. So I encourage you to make some matrices and try multiplying them, verify some of the equations we went through, and verify some of the rules about the size of A that can be multiplied by the size of B. And you can do that for vectors as well as matrices. So I'd like to end this video and continue on with some more matrix operations in the next video.